Moments are a fascinating concept that encapsulate the interplay between force and distance, and they are pivotal in understanding how objects can be balanced and manipulated in our everyday lives. To grasp the essence of moments, we need to delve into the fundamental definition. A moment is the turning effect produced by a force acting at a distance from a pivot point. This distance is often referred to as the lever arm, and when we multiply the force applied by this distance, we obtain the moment. Now, let's consider a seesaw, a classic example that many of us encountered in our childhood. When you sit on one end of a seesaw, you exert a downward force due to your weight. To determine if the seesaw is balanced, we must calculate the moments on either side of the pivot, which is the central point of the seesaw. For the seesaw to be in equilibrium, the moments on both sides must be equal. This means that if you weigh more, you need to sit closer to the pivot, while a lighter person can sit further away. The equation governing this balance is quite simple. The moment on one side, which is the weight multiplied by the distance from the pivot, must equal the moment on the other side. This principle not only applies to seesaws, but is a fundamental aspect of engineering and physics, helping us design stable structures and mechanisms. Understanding moments leads us to the broader concept of levers, which are simple machines that allow us to do work more efficiently. A lever consists of a rigid bar that pivots around a point called the fulcrum. By applying a force at one end of the lever, we can lift a heavier load on the other end with less effort. This is possible because the lever amplifies our input force based on the distances from the fulcrum. The longer the lever arm on the side where we apply our force, the greater the mechanical advantage we gain. In essence, levers allow us to trade off force and distance, making it easier to lift heavy objects by reducing the amount of force we need to exert. The concept of moments and levers seamlessly connects to gears, which are another ingenious application of these principles. Gears are circular wheels with teeth that interlock with one another, and they transmit rotational effects from one gear to another. When one gear turns, it causes the adjacent gear to turn in the opposite direction. The moment created by the force applied to one gear is transferred through the interlocking teeth to the next gear. The size of the gears plays a crucial role in this transmission. Larger gears require more force to turn but provide greater torque, while smaller gears can turn more quickly but require less force. This interplay allows machinery to function efficiently, enabling us to perform tasks ranging from simple clock mechanisms to complex automotive engines. In summary, understanding moments provides us with powerful tools to analyze and manipulate our physical world. By calculating moments, we can determine the balance of seesaws, leverage our efforts with levers, and harness the rotational effects of gears. These principles are foundational in physics and engineering, allowing us to design a wide array of devices and systems that enhance our capabilities. From playgrounds to manufacturing plants, the concepts of moments, levers, and gears are intricately woven into the fabric of our daily lives, showcasing the beauty of physics in action. The next time you see a seesaw, lift a heavy object with a lever, or observe the turning of gears in a machine, remember that these moments are not just abstract ideas. They are the very essence of how we interact with the world around us.